Okay, so we started to look at the icosahedral symmetry in the last class, and we determined the proper rotational axes. So next we can look what mirror planes there are. And there's actually only one kind of mirror plane, and you see one of these mirror planes here. And you see that these mirror planes, they contain two edges. So we can again pretty easily derive how many mirror planes we have. We could determine that we have 30 edges. You would expect that we have 30 over 2 speed rotor, 15 mirror planes. Okay. So these mirror planes are not categorized either as vertical, nor are they categorized as horizontal mirror planes. The reason is not entirely clear. I didn't find this in any textbook, but when you look at them, you can see that they have both horizontal properties and both vertical properties, because some contain the principal C5 axis, but also stand perpendicular to one C5 axis. All right. So what other symmetry elements and operations do we have? We have an inversion center. That's again very easy to understand. That inversion center is in the center of the icosahedron. So as we carry out the symmetry operation, we move all the points through the inversion center to the other side. Okay. All right. We always have only one inversion operation per inversion center, so that makes it very easy to determine the number of symmetry operations. We have just one. Okay, so now let's go to the rotation reflections, and these are always a little bit harder to understand. So the rotation reflection of the highest order is the S10 rotation reflection, and you see one of them here, and the respective improper rotational axes, they stand where the C5 proper rotational axes are, meaning that they're going to two opposite vertices of the icosahedron. But instead of rotating by 72 degrees, we now rotate only by 36 degrees. After that, our icosahedron does not superimpose yet. We have to reflect at a mirror plane perpendicular to the improper rotational axis in order to make the icosahedron superimpose. So again, for some reason, I have some problems with the animation, but here you see how this actually works. So essentially, this rotation reflection works because you see that the two pentagons, this one here, that stands perpendicular to the S10, and this one here, that also stands perpendicular to the S10 are in a staggered orientation. So for that reason, we can rotate by 36 degrees and then reflect and make the two pentagons superimpose. Okay, so these 2 points here, this one and this one, does not move during the rotation, but these 2 points, they exchange as we carry out the reflection. So again, we can ask, well, how many of these S10 improper rotation reflections will we have? Well, we will have as many as we have C5 proper rotational axis, because the S10 stand in the same position as the S5. So how many were these? If you remember this, these were 6. Okay, so we have 6 of these S10 improper rotational axes, and here you see them all. So now, how many symmetry operations are associated with these symmetry elements? So in order to determine this, we first have to recognize that we have here rotation reflections with an even order. 10 is an even number. So which operations do we have to consider, therefore? We have to consider the operations from S10-1 to S10-10. So we know that the S10-10 is identical to the identity, but what about the other 9? So the thing is that the S61 is unique, the S63, the S10-1 is unique, the S10-3 is unique, the S10-7 is unique, and the S10-9 is unique. Okay. The others are not unique. So for instance, the S10-2 can be expressed by C5-1, again, because when we reflect 2 times, this is the same as not reflecting at all. So we actually rotate only by 2 times 36 degrees, and that's 72 degrees. So for the same reason, the S10-4 is the same as the C5-2. So again, reflecting even number of times, in this case 4 times, is the same as not reflecting at all. We only rotate 4 times around 36 degrees, so that's the same as only as rotating 2 times around 72 degrees. So then one can show that the S10-5 is the same as the inversion. The S10-6 is the same as a C5-3. That's again because we reflect an even number of times, so we don't reflect. So we actually just rotate. So we rotate in this case 6 times 36 degrees, and that's the same as rotating 3 times 72 degrees. And last but not least, the S10-8 is equal to the C5-4. Again, we reflect an even number of times, so this is the same as not reflecting at all. We rotate 8 times by 36 degrees, and that's the same as rotating 4 times by 72 degrees. Okay, so now how many operations do we have overall? Well, per symmetry element, we have 1, 2, 3, 4 independent symmetry operations to consider. So we have overall 4 times 6, which is equal to 24 as 10 operations here. Okay, so what other improper rotations do we have? Well, there are also S6 improper rotations, and they actually stand where the C3 proper rotations are. Namely, they go through the center of 2 opposite triangular faces. So this S6 here enters the icosahedron through this triangular face, and it leaves the icosahedron here to this opposite triangular face. Okay, now how do the points get transformed? So let's see if I can get my animation to work again here. All right, so in this case, we rotate by 60 degrees, and then reflect here at this mirror plane. So we can understand that this symmetry variation works when we consider that, well, this triangular face here, to which the S6 improper rotational axis enters, and this triangular face here, through which the S6 axis leaves, they stand in a staggered orientation to each other. Okay. Therefore, when we rotate around, well, half of 120 degrees is equal to 60 degrees, and then reflect, we can actually move this triangular face into this position, and that triangular face moves into this position. And all the other points in the polyhedron also superimpose. So now how many of these S6 axes do we have? Well, we have as many as C3. Remember, we had 10 C3, so therefore we have 10 S6. We can again review why we had 10 C3. That's essentially because we have 20 faces, and we need 2 faces per improper rotational axis, and 20 over 2, that gives just 10. So now, how many operations do belong to these symmetry elements? So again, our improper rotational inflection has an even order, and that means that when we consider the operations between S61 and S66, whereby S66, as we know, is the identity. So that leaves us everything between S61 and S65. So are they all unique? The answer is no. So for instance, the S62 is equal to the C31. That is again because we reflect an even number, which is the same as not reflecting at all. So we actually just rotate, and rotating 2 times 60 degrees is equal to 120 degrees. Okay, and that's the same as a C31. So the S63 is equivalent to an inversion, and the S64 is equivalent to a C34. Again, we have to put it straightforward to understand. We again reflect an even number. That's as though we do not reflect at all. So in this case, we rotate 4 times 60 degrees, which is 240 degrees, and it's the same as 2 times 120 degrees. Okay, is there anything else to consider? The answer is no. Now we got it all. So see here again, all the symmetry elements that we have found listed. And you see here all the symmetry operations that belong to them. And you see these are really quite a few. So overall, we have 120 symmetry operations in the icosahedral point group RH. So that makes the icosahedral point group the point group the highest symmetry. So there's also a rotational subgroup to the icosahedral point group RH, just like for the octahedral case. So, and that's then called the group I. And again, it's called a rotational subgroup because all the proper rotations of the point group IH still exist, but all the other symmetry operations are gone. Okay. So that means that we still have the 6C5, the 10C3, and the 15C2, but we do not have anymore the 15 mirror planes, the inversion center, the 6 improper rotational reflections, and the 10 S6 improper rotation reflection. So this point group is fairly rare, but there are a few examples. So you see here one example. So this polyhedron is called a snap dodecahedron. And you see that this polyhedron contains pentagons again, and the 5-membered 5-fold principal axis, they actually go perpendicular to these 5-membered rings. but you see that these 5 membrane rings are then surrounded by triangles. Okay, you see here that they are surrounded by triangles. Okay, and then again you will find a pentagon, for instance, here and here and here and here and here. So basically, the pentagonal faces are separated by triangles, and that gives a snub dodecahedron that has the rotational subgroup I. Okay, then let's move over to the next presentation. We still have a few things to say about the. No, we actually finished. I will explain what I just thought of after the other point groups. So now let's leave the high symmetry point groups. We have already discussed the low symmetry point groups, so that leaves now all the point groups that are in between low symmetry and high symmetry. And the first class that we want to consider is what is called the rotational groups. And the rotational groups have the property that they have one principal axis, which are proper rotations. So in the most simple case, they do not have any other symmetry elements besides the identity. So only one proper rotational axis, but no other symmetry element. An example for that is the hydrogen peroxide molecule H2O2, and you see here the structure. You see that the structure is actually not coplanar. And that is because the electron lone pairs here at the oxygen consume more space at the hydrogen sphere, and therefore they try to achieve the greatest distance. For that reason, the hydrogens also bend away from each other. So we say that the hydrogen peroxide molecule has the so-called roof structure. So besides the identity, the hydrogen peroxide has only a C2 axis as the principal axis. Okay, so as you carry out that symmetry operation, and again, there was supposed to be an animation to work, and I don't know why this is always these difficulties. So regardless, when we rotate around the C2 axis here, well, we swap up the positions of these oxygens and we swap up the positions of these two hydrogens. Okay, but there's no other rotational axis. There's also no mirror plane and also no improper rotation. So these are called the cyclic groups, and they are denoted Cn. So in this case, our rotational axis is the order 2. Therefore, point of H2O2 is C2. Okay, so now we can add other symmetry elements to that principal axis. So for example, we can add vertical mirror planes. So when we add vertical mirror planes, then we must always add n vertical mirror planes, whereby n stands for the order of the principal axis. So for example, if we have a principal axis of the order 3, then we must have 3 vertical mirror planes. When we have a principal axis of the order 4, then we must have 4 vertical mirror planes. So these are called the pyramidal point groups C, N, V, because the structure of these molecules derived from a pyramid. So for instance, the ammonia molecule, which derives from a trigonal pyramid is in the point group C3V. Okay, if in this case the identity, the C3 principal axis, and 3 sigma V mirror planes. All right. So one can also, of course, have other n-gonal pyramids. So as I said before, the NH3 molecule derives from a trigonal pyramid. Okay, it is this structure here. Okay, the C3 axis goes actually to the nitrogen atom, and the base of the pyramid made of these 3 hydrogens, and the vertical mirror planes, they go to the 3 nitrogen hydrogen bonds here, here, and here. But in addition to a trigonal pyramid, we can of course also think of molecules that derive from a square pyramid, for instance, or in more general terms, an n-gonal pyramid, whereby n defines the number of vertices in the base of the pyramid. So there's one particular case, which is the case when the number of these vertices approaches infinite. Okay, then we arrive at the linear group C infinite V. And the structure which is associated with this point group is a cone, as you can see here. So a cone has a proper rotational axis with infinite order. Okay, that means that we can rotate here this cone around an infinitely small angle, and then our object imposes. So now the number of vertical mirror planes must be equal to the order of the principal axis. So the order of the principal axis is in this case infinite. Therefore, we must have an infinite number of vertical mirror planes. And these vertical mirror plates will all contain the principal axis. Okay, so you see here an example molecule. So generally, polar linear molecules belong to the point group C infinite V. For instance, carbon monoxide, HF, N2O, and HCN. You see here HCN, an example. Here's the hydrogen, here's the carbon, and here's the nitrogen. And you see, well, we have here an order going through the bond, axis going through the bonds, and that axis has an infinite order. But we also see that we have an infinite number of vertical mirror planes that contain this axis. Okay, now we have also the possibility to add a horizontal mirror plane to our principal axis, and not vertical mirror planes. So these rotational groups are called the so-called reflection groups, C, N, H. Okay, so it's the point group symbol. Whereby N again stands for the order of the principal axis. So you see here actually an example. So this is the trans fluorodifluorodiazine molecule. You see that molecule here is planar, it lies within a plane. And we have a C2 axis as the principal axis in this case. And as we carry out symmetry operation, well, we swap up these two nitrogens here, but also these two fluorine atoms over there. Now, in addition to that, we have a horizontal mirror plane. So this plane here. Why is it horizontal? Because it stands perpendicular to the C2 axis. When we carry out the symmetry operation, we do not move any atoms, but like I said before, this doesn't matter because we still move points in the object. For instance, well, the hemispheres that lie above that mirror planes will lie below that mirror plane after the execution of the symmetry operation. Those that lie below the mirror plane lie above the mirror plane after the symmetry operation. So the presence of the horizontal mirror plane also implies that there's an additional improper rotation inflection, which is the same order as the proper rotation. So in this case, the order of the proper rotational axis is 2. Therefore, we must have an S2 in addition. And remember, an S2 is the same as what? And you can also say something. Okay, that's an answer. An inversion. Yes, correct. Yeah. So we can easily see that there's an inversion center here in the middle of the nitrogen-nitrogen bond. So as we carry out the symmetry operation, we move this fluorine through the inversion center to the other side, this fluorine through the inversion center to the other side. We also swap up the positions of the nitrogen atoms. This way. Yeah? So overall, we have here the identity, the C2, the inversion center, and the sigma H for this particular molecule. All right. So now we can also add NC2 axis to our principal axis. And then we arrive at so-called dihedral groups. In the most simple case, there are no other symmetry elements but the principal axis and the NC2 axis. So here's an example. So here, this molecule, this is actually a twist oscillator iron complex, which has the symmetry D3. Okay. So D now stands for dihedral and implies that, well, we have 3 C2 axes in addition to our principal axis with the order 3. Okay. So now, where are these symmetry elements? You see that the C3 axis stands actually here perpendicular to the plane of the screen. And you see here the 3 C2 axes, okay, which actually bisect the carbon-carbon bonds here, here, and here of the oscillator ligand, respectively. Okay. So now you see how the atoms transform. So we've just carried out C3 symmetry operation. But now in addition, we can also have the C2 symmetry operations. Okay. And in this case, we have rotated on this C2 axis in order to make molecules superimpose. So these are the properties of the point group type dn. So then again, we can add mirror planes, and we can add the vertical or horizontal mirror planes to a dihedral group. And when we add a horizontal mirror plane, then we arrive at the so-called prismatic groups of the type DNH. We call these prismatic groups because the respective molecules derive from angular prisms. Okay? And you see here a few examples. So this here would be, for instance, a pentagonal prism made of two pentagons that are in eclipsed orientation. You see here a hexagonal prism with two hexagons here and here in an eclipsed orientation, and here that would be a prism with a heptagon, the two heptagons that stand in an eclipsed orientation. You can easily see that these prisms have a mirror plane. Okay, so these horizontal mirror plane, and these mirror planes stand perpendicular to the base planes of the prism. Okay? But so they stand parallel, not perpendicular, parallel to the base planes of the prism. And they basically bisect the prism halfway. Okay. So now when you have the horizontal mirror plane, then that automatically means that you also have some other symmetry elements. In particular, you will also have to have an n number of vertical mirror planes, as well as improper rotational axis that has the same order as your proper rotational axis. Okay, so here is an example. Here we have the molecule PF5. So this molecule has a trigonal bipyramidal shape and belongs to the point group D3H. You can easily verify that it belongs to the point group D3H. So where is the principal axis? Well, the principal axis stands here. It goes actually between through the two axial fluorine atoms. So now, in addition to that, we have three C2 axes, and that basically satisfies the requirement for a dihedral group. And now these C2 axes, they go through the equatorial fluorine phosphorus bonds. See the first one here, and you see the second one here, and you see the third one over there. Okay. So now, where's our horizontal mirror plane? You see that our horizontal mirror plane is here. It actually lies within the equatorial plane, and that means that it stands perpendicular to our C3 principal axis. So as we carry out the respective symmetry operation, of course, we do not move the equatorial atoms, but we swap up the positions of the axial atoms. So now, in addition to that, we must also have an n number of vertical mirror planes. And you see those actually all over here. You see that they all contain the C3 principal axis. So this one here, okay, contains the C3 principal axis. So this one here does, and the last one does that as well. So each of these vertical mirror planes go through one phosphorus fluorine bond within the equatorial plane. So So the first one contains this bond, the second one contains that bond, the third one contains that bond. All right. Then another requirement is also that we have an improper rotational reflection, which is the same order as the principal axis. So that's in this case NS3. So we can rotate not only 220 degrees, but we can also mirror perpendicular to that in addition to make our molecule superimpose. That is because in addition to C3, we also have sigma H. Okay. So then there's one particular prismatic group, which is the linear group D infinite H. So this group results when the order of the principal axis becomes infinite. And the object that belongs to the linear point group D infinite H is the cylinder. Okay, you see that in a cylinder, you have a principal axis that basically stands perpendicular to these two faces of the cylinder. And of course, when we have a circle, then we can rotate around an infinitely small angle. Sorry. And our object will superimpose. So that now implies that we have an infinite number of C2 axes. Okay, and these C2 axes stand perpendicular to the infinite axis. You see actually one of them here. They go all around the cylinder. You can see this better here in the example molecule, the CO2. It's kind of a cylindrical molecule. Here you have again here the principal axis, infinite order. And you have here all the infinite C2 axes. So of course we need to have the sigma H horizontal mirror plane, and it just bisects the cylinder, okay, as well as it would bisect this CO2 molecule. We also have to have now an infinite number of vertical mirror planes which contain the principal axis. You see these here as blue cylinder. And in addition, we also have to have an improper rotational axis with the order infinite. That is because of the presence of the C infinite axis and the sigma H mirror plane. Okay. What else do we have? We also have the dihedral point group type D and D. So in this case, we do not add a horizontal mirror plane to the principal axis and the C2 axes. We add vertical mirror planes. And these vertical mirror planes are dihedral mirror planes because they have the property to bisect the angle between two adjacent C2 axes. Okay. Hence the name of the point group D and D. So here you see an example. So this is the ethane molecule in a staggered conformation. So we see here, there's the C3 axis. Okay. And now we have the C2 axis here, here, and here. Okay, in the 3C2 axis, they're going through the middle of the carbon-carbon bond, but they also stand perpendicular to the carbon-carbon bond. And they bisect the angle between two hydrogens. Okay, you can actually see this here. And this projection. So here we look at the FM molecule along the C3 axis. So you see here that the C2 axis, they bisect the angle between two hydrogen atoms that belong to different carbon atoms. Yeah, that's the first one, the second one, and that's the third one here. Okay, so now in addition to that, you also have vertical mirror planes. And these vertical mirror planes, you see this again clearly here, they contain the C3 axis. Okay, so this is the first vertical mirror plane. Here. This is the second vertical mirror plane. Here. And this one here is the third vertical mirror plane. You see they all contain the C3 axis. So all of these mirror planes contain two carbon-hydrogen bonds that belong to different carbon atoms. Okay, so for instance, this vertical mirror plane here contains this carbon-hydrogen bond and this carbon-hydrogen bond. Okay, you can see this again pretty clearly over there also. So we have here, for instance, a vertical mirror plane, okay, that contains this carbon-hydrogen bond here and this carbon-hydrogen bond. So this vertical mirror plane contains this carbon-hydrogen bond and this carbon-hydrogen bond. And this vertical mirror plane over here contains this carbon-hydrogen bond and this carbon-hydrogen bond. So now you see that these vertical mirror planes bisect the angle between two C2 axes. For instance, this vertical mirror plane here bisects the angle between this and this C2 axis. Okay, so you see actually the C2 symmetry operation carried out here. Okay, so in this case we have rotated around this C2 axis, and you see that the molecule is superimposed. All right. So overall, we have in this case the identities, the C3, the 3C2, and 3 sigma D. We also must have an S6 in this case and an inversion center, which is generated through the presence of the other symmetry elements. Okay. Then last but not least, we have a kind of a strange type of point group. It's denoted S2N. And in this case, we have only a principal axis as well as an improper rotational axis with the order 2n. So the order of the improper axis is 2 times the order of the proper axis. We have the identity, but beyond that, we have no other symmetry except perhaps an inversion center. So you see here for an example of a molecule that belongs to the point group S4. So this molecule actually has a C2 axis and an S4 axis, as well as but no other symmetry element. So you can relatively easily see this. when you actually look at the molecule more in this perspective, you see that we have here cycloocta tetraene ring. So this ring is not planar. You see that two carbon bonds actually lie below the plane, these two, and two carbon-carbon double bonds lie above the plane. Okay, so in this view here, we see here the carbon-carbon double bonds lying below the plane, and the ones above the plane, they stand perpendicular here. So now, in addition to that, we have methyl groups attached. Okay, so these two here, they lie below the plane, and these two here lie above the plane. And there are also 4 hydrogens. These two here lie above the plane, and these two here lie below the plane. You see this again over there. You have here these two methyl groups which lie above the plane, and the other two methyl groups which lie below the plane. So we see here first hydrogen, and here a little bit hidden the second hydrogen above the plane. And here we have the first hydrogen and the second hydrogen below the plane. So there's a C2 axis, okay? Because when we rotate by 180 degrees, we make these two carbon double bonds superimpose, and these two double bonds superimpose. Okay, and we move this hydrogen to position of this one, and this hydrogen in position of that one. And this methyl group moves in position of this one, and this methyl group moves in position of that one. So this methyl group here moves into position of this one, and this methyl group here moves into position of that one. All right, now in addition to that, we also have the S4. Okay, so if we carry out the S4, again, that was supposed to animate, but it doesn't for some reason. Then, for instance, when you put yourself onto this methyl group and rotate by 90 degrees, then it's actually underneath this methyl group. Okay, so it doesn't impose yet, but we only need to mirror it from below the mirror plane to above the mirror plane to make it superimpose with that one. Okay, and this methyl group, for instance, would rotate into this position by 90-degree rotation, but without the reflection, it's lying actually above that methyl group here. You need to apply the reflection operation so that the superposition is complete. So you can do the same exercise also with the hydrogens here as well as the carbon-carbon bonds, and you will always find that you require 90-degree rotation in combination with the reflection in order to make the molecule superimpose. So therefore, in addition to the C2, we have the S4. But other than that, we do not have a symmetry element. Okay, then let us stop at this point.